In this lesson, we'll talk about minimum and maximum values of a given function. To start with, here we have a graph of y is equal to f of x. I would like to use this graph to find the absolute minimum and absolute maximum y values of this function on the closed interval from -2 to 6. Closed meaning it contains both of the endpoints. If we start with the absolute min, that means the smallest overall y value from here to here. I can see that that has to be this spot right down here. The absolute minimum y value is -2, and it actually occurs at x is equal to -2. So there's exactly one absolute minimum, the smallest possible y value, and it occurred at this endpoint of -2. Now, what about the absolute maximum, or the absolute max? Where is the largest overall y value from -2 to 6? And that is right here, and it appears to be 7. So where's the absolute max, the largest overall y value from -2 to 6? This occurs at x is equal to 1. And that is the only one from -2 to +6. So when we talk about an absolute max and an absolute min, we're looking for values that are either the largest overall or the smallest. Now there's another type of min and max values that you can have, and those are called local minimums and local maximums, or just for short, local mins and local maxes. When we talk about these types of values, we're talking about the interval from -2 to 6, but not including the endpoints. So we'd call this an open interval. So from here to here, not including -2 and not including +6, where are the local mins and local maxes? Let's start with the local min. A local min means it's the smallest y value within this interval around some given x value. And I can see there's one right here. At x is equal to 3, there is a local min, so I'm going to jot that down. Why is this a local min? Well, it's certainly not the smallest y value. There's smaller y values over here and here. But as long as you're around 3, it's the smallest value in this region. So that's what we mean by local. It doesn't mean overall, like absolute. It just means in some region around this number. So at x is equal to 3, there's a local min value. Now, what about a local maximum, or just a local max? This is a largest y value around some x value within the interval from -2 to 6. And I think there's going to be two of them. There's one here at 4. At 4, as long as you're near 4, there is a largest y value of 5. So at x is equal to 4, there is a local max. So I'll put a 4 here. And actually, there's also a local max at 1. It turned out that this was an absolute max, but it's also a local max because at this one spot, as long as we're close to 1, there is a largest value there. So not only is 4 the location of a local max, so is 1. So just to recap, the idea behind absolute min and max means it's the largest overall value on some closed interval. A local min and a local max means it just has to be the largest or smallest in some region around a number, and here we will always exclude the endpoints. The main goal of this lesson is to find a procedure for locating the absolute min and max, so determining when they exist and how to find them. And for this reason, I'd like to make an observation. The observation is, when looking for an absolute min or an absolute max, you only need to check the endpoints and places where the derivative is either equal to 0 or does not exist. Notice in this example, the absolute min occurred at an endpoint of -2, and the absolute max occurred at this spot right here. This spot is where the derivative is equal to 0, and this spot over here occurred at an endpoint. You would never have to check any spot, let's say, in between here and here, because the function is always increasing. So you need to check where the graph might change directions, which is here, where the derivative is 0. Another way a function or a graph can change directions is if the derivative is undefined. So if you can locate these, in this case, 1, 2, 3 places, as well as 4 or 5 the endpoints, there's only really 5 spots on this graph that you have to check when looking for the absolute min and max. I will summarize these ideas in a theorem that's on the next slide. To show that absolute mins and maxes exist on a given function, we can use the extreme value theorem. Extreme values meaning the absolute mins and maxes. So if you have a function f of x that's continuous and it's on a closed interval, that is enough to say that there will be an absolute min and an absolute max. And that has to fall on the interval that you're working with from a to b. So said another way, on this interval, you can find a c and a d where f of c is the absolute min and f of d is the absolute max. Also, as was stated on the previous slide, places where the derivative is either 0 or undefined will help you figure out where these mins and maxes are located. And for this reason, I'll introduce a definition. A critical number is any number c where the derivative of that number is either equal to 0 or it does not exist. Let's combine all these ideas in example 1. Here I have this function x cubed minus 6x squared plus 9x plus 2, and we'll define it on this closed interval. First, I want to find all the critical values of this function, and then use these numbers to find the absolute mins and maxes. I'll first note that f is continuous, as it is a polynomial, and this interval 0.5 to 3.5 is closed. And therefore, by the extreme value theorem, I know a min and a max, an absolute min and max, must exist on this function. So how do we find them? Step 1 is let's find the critical numbers. We do that by taking the derivative of this function and determining where it is either 0 or where it does not exist. So let's see, we'll find the critical numbers by first taking the derivative of this function. And the derivative is 3x squared minus 12x plus 9. And I want to set this thing equal to 0 or figure out where it is undefined, where it does not exist. Well, this thing always exists. It's a polynomial. So we only have to check this, where it's equal to 0. So where does 3x squared minus 12x plus 9 equal 0? So before I try to factor this thing, I'm going to divide through by 3. And this will change this equation to x squared minus 4x plus 3 is 0. I think this factors. Okay, it factors with an x and an x, a minus 1 and a minus 3. So the two places where this is equal to 0 is positive 1 and x is equal to positive 3. These two numbers, when put in place of x, make these factors 0, so it makes the entire equation 0. So these things here are critical numbers. When looking for an absolute min and max, the only thing that you need to check in a table of values is the endpoints and the critical values in the original function. So that is, I'll check the endpoint of 0.5, the critical number 1 and 3, and then the other endpoint of 3.5. I'm checking this on the original function because the original question is, can we find the min and max values on this function? It has to be one's a min and one's a max between these 4 values. So the rest, I'm just doing this directly in my calculator. So at 0.5, I get 5.125. At 1, I get 6. At 3, I have 2. And at 3.5, I have 2.875. So what does this mean? My max value, the absolute max, which I'll just put absolute like this, max, has got to be at this point here. At x is equal to 1, it achieves a y value of 6, and that is the biggest among these 4 different numbers. And where is the absolute minimum? That has to be this here. So this is the absolute min. And the reason for this is the smallest y value among these 4 numbers. So just to state it separately, the absolute min is the y value of 2, and it occurs at x is equal to 3. And the absolute max is y is equal to 6, and that occurs at x is equal to 1. So in this interval, there's infinitely many numbers, but you only need to check the endpoints and the critical numbers. Between those numbers, one has got to be the largest and one has to be the smallest. So to recap, to apply the extreme value theorem, we needed two things: a continuous function on a closed interval. Now the question is, what if your function is not continuous? Well, what if the interval isn't closed? I have both of these ideas represented in this picture down here. It's the same graph that we started with, except here at 1, I made the function not continuous, and the interval is open at -2, meaning we don't include it, although it is closed at 6. So here I changed it a little bit. This is not continuous, and the problem occurs at x is equal to 1, right here. The value of the function is 5 instead of at 7. And the interval from -2 to 6, it's not closed. Will there be a min and a max? And the answer is, in this case, no. In some cases, there might be, but in general, you can't say this is always true. So if we look at this picture here, the fact that this is not continuous at 7 means there's no max value. The max value should be 7, but there's a hole here and it jumps down to 5. So there's actually no number where you get a largest value because there's a hole here. So here, there is no absolute max. This y value of 7 is never on the graph. And these are always getting larger and larger and larger, but they never get to 7 for sure. There is also no absolute min, and that's because of what's happening over here. The graph gets closer and closer to -2, but it never actually is equal to it. And the reason for this is because we're not including the endpoint of -2. So there's also no absolute min. This is something to look out for. When applying this theorem, you have to have continuity. You have to have that this interval is closed, because otherwise you might not be able to find an absolute max or an absolute min. Let's try this idea out in example 2. I'm going to sketch a graph of f of x is equal to the natural log of 4x. And I'm going to do this on the interval from 0 to 2. Now, this is not closed. So I'll say this is not closed. And the reason is because we are including 2, but we're not including 0. So if you go to sketch a graph of this function, so 1 and 2 like this, here's 0, the natural log of 4x looks like this. At 2, which we're allowed to use, it's a little bit greater than 2, so that's like right about here. At 1, it's equal to 0, and then it approaches this as a vertical asymptote, so the graph looks like this. So here's a graph of the natural log of 4x. This is continuous, and that's because we're never actually using the number 0. It's just everything greater than 0 all the way up to and including 2. So are there any local max and mins? Or what about absolute max and absolute mins? If we start with the absolute mins and maxes, we're allowed to use the endpoints, except for this one just because we're excluding it from this interval. So in that case, there actually is a largest overall y value, and that occurs at x is equal to 2. So there is an absolute max. And the exact value of it occurs at x is equal to 2, and that value is f of 2, which is the natural log of 4 times 2, which is the natural log of 8. So there is this value that is an absolute max, and it occurs at this value. And I'm figuring this out just by looking at the graph of the function. This is clearly the largest y value. Now, is there an absolute min? And the answer is no. Because we're not including this endpoint, this graph actually drops down towards minus infinity. So actually, I'll state the limit as we approach 0 of this function, which I'm just going to call f of x, from the right side goes to negative infinity. So there's actually no smallest y value because this thing keeps going lower and lower and lower. And I really feel that this is justification enough just to say by looking at the graph, This thing's going down forever, so there's no smallest value. Well, what about a local min and a local max? Let's start with local max. Now, there's an absolute max because there's the largest value here. The way we define local mins and maxes, these cannot occur at endpoints of an interval. They must be within the interval itself. So you're only allowed to use, in this case, stuff between 0 and 2, not including 2. So is there a local max? No. This thing keeps getting larger as we go in this direction. It keeps dropping towards negative infinity as we go in this direction. So again, just by examining the graph, there is no local max. And is there a local min? And the answer to this is also no. This graph keeps going down forever. It doesn't ever level off, drop back down, then go back up. So for this reason, there is an absolute max, but there's no absolute min, nor a local max, nor a local min. In example 3, let's find the absolute min and max of this function f of x on the interval from 0 to 7. So first, I'm going to note that this interval is closed. It contains both endpoints. Also, f of x, which equals x over x squared plus 25, it's rational, and the denominator is never 0. What does this all mean? It's continuous. So we have a continuous function on a closed interval. By the extreme value theorem, an absolute min and max must exist on this interval. So how do we actually go about finding it? The process is find the critical numbers, put those and the endpoints of this interval in a table. Whichever is the largest is the absolute max. Whichever is the smallest is the absolute min. So let's start by finding the critical numbers. To do that, I need to take the derivative. By the quotient rule, the derivative of f is equal to the bottom, which is x squared plus 25, times the derivative of the top, which is 1, minus the top times the derivative of the bottom, which is just 2x. And this is all divided by x squared plus 25 all squared. Now, the critical numbers of the function f are wherever this is equal to 0 or undefined. And this is always defined, so I'm only going to check to see when this is equal to 0. Let's simplify the function. F prime of x is equal to, I just need x squared plus 25, and then minus 2x squared. This is all over x squared plus 25 squared. X squared minus 2x squared is a negative x squared. So the derivative is really 25 minus x squared in the numerator. And we only need to check where this is equal to 0, since this thing is always defined. That means we only need to check where the numerator is 0. So to find the critical numbers, I'm going to set the numerator 25 minus x squared equal to 0. When I add x squared to both sides, I get this. And by taking the square root of both sides, we get that x on the right is equal to 5 on the left, but technically a plus or minus. So there are two numbers that make the derivative 0. Notice that the interval is from 0 to 7. We do not need to consider any critical numbers that fall outside of this interval. And for this reason, for the critical numbers, I'm actually only going to use x is equal to 5. And the reason for this is negative 5 is not in the interval from 0 to 7, so we will not use it. Now, when it comes to figuring out the absolute min and max values of the function f, I need to check three numbers in a table: 0, 7, the endpoints, and any critical number that falls within the interval itself. So in a calculator, I'm going to enter in my function, the original function, f of x. So not the derivative, but the original function. I'm going to check the endpoint of 0, the critical number that falls between 0 and the other endpoint, 7. So let's see what we get. Between these three numbers, by the extreme value theorem, there must be a largest and there must be a smallest The largest is the absolute max, and the smallest is the absolute min. So I get 0, 5, and 7. Okay, I get at 0, it's equal to 0. At 5, it's equal to 0.1, or a tenth. And then at 7, it's approximately equal to 0.09459. So what does this all mean? This means this is the min. It is the smallest of the three y values. And this is the max. It's the largest of the three y values. So there is an absolute min, and there is an absolute max. I will state those points. I'll say the absolute min is the 0, 0, and the absolute max is the 0.5, 0.1. So these are the answers for this problem. Okay, last question, same idea. I want to find all absolute min-max values of this function on the interval from 0 to 1. And here I have an absolute value of 2 minus 7x. I'll first note that, well, 0 to 1 in this case is closed. It contains both 0 and 1. The function f of x, which is the absolute value of 2 minus 7x, is continuous. It's continuous because the absolute value function is continuous. 2 minus 7x is a line, which is also continuous. And if you compose continuous functions, they are continuous as well. What does this all mean? By the extreme value theorem, the absolute min and max of this function on this interval must exist. So what's our process for figuring this out? Well, the process is you take the derivative of the function, you set it equal to 0, and you also check to see where it does not exist. Those are your critical numbers. You check those and the endpoints, and that will allow you to find the absolute min and max. But how do you actually take the derivative of this function? We don't really have a nice rule for taking the derivative of the absolute value function. For this reason, I'm just going to go ahead and sketch a graph of this equation from 0 to 1. So let's see. F of 0 is equal to the absolute value of 2 minus 7 times 0. That means f of 0 is the absolute value of 2, so it's just 2. If we check the other endpoint of 1, that's the absolute value of 2 minus 7 times 1. So f of 1 is 2 minus 7, which is minus 5, and in absolute value is equal to positive 5. And this should be a V-shaped graph. So it should go down and then eventually go back up. So it should look like this. Here's an okay sketch of this function. Whereas this spot here, in terms of critical numbers, the derivative of this thing is never 0, but it actually does not exist, and that occurs wherever this number is. Where's this spot? That's where this function is actually equal to 0. So if you want to find where the derivative does not exist, you can actually take the original function and set it equal to 0 like this. So the function equals 0 is where the derivative is undefined, and that's where the thing inside the absolute value is equal to 0. To find the x, I'll add 7x to both sides, and then I'll divide by 7 to get 2/7 is x. And that's this location here. So in a table of values, if you check the endpoints, as well as 2/7, between those three values, one has to be the smallest and one has to be the largest. Well, we already have all these values. The function at 0 is 2. The function at 1 is 5. And the function at this critical number, 2/7, is 0. That means this is the min, and this is the max. So the absolute min is at x is equal to 0. And the absolute max is at x is equal to 2/7. And that's it for this problem.